Hi. So what we're going to work on today is going to be a method that involves computing the volumes of three-dimensional objects using shells instead of using washers like we used in the last section. So what I mean by shells is instead of thinking about an object and slicing it into cylindrical pieces that we can estimate the volume, like a loaf of bread, instead this is more like the way that an onion's layers are set up, where an onion is constructed of very thin layers that build out the whole shape of an onion. So if you could calculate the volume of each sort of thin layer, then you could add up the volumes of all those thin layers and you ended up with a volume of the entire shape. So it's called the shell method because the objects that you're dealing with are thin and they're going to be cylindrical but in a different way than in the previous section. So the first thing we're going to talk about is why you wouldn't necessarily want to use washers or disks on a problem and why another method is going to be better. And that's going to be easiest to show by way of an example. So let's just suppose that we had something that looked like this. So we've got this parabola. Let's say for the sake of argument that this parabola is something like y is equal to x minus 2 squared. And let's bound the region by putting y equals 1 on top of it. And so that's going to mean that we're going to have a cap right here. And so the region that we're looking at looks like this. This has a vertex at 2. And now let's suppose that we take this shape and we spin it around the y-axis. So we're going to rotate it this way. Well, what do you get? Well, you're going to get sort of this donut-looking shape, I guess, a half of a bagel. So you're going to have one piece that looks like this, and another piece that looks like this, and then there's going to be an interior circle, and then there'll be an exterior circle on the top, and then the bottom kind of wraps around like that. So if that helps you see a picture of what it is that we're looking at, you can think of it as half a bagel. So the problem is if you try to cut this thing up into washers, right? So remember that washers are perpendicular to the axis of rotation. So if the rotation goes this way, then when we think about disks, when we're bread slicing, we're slicing this way. If we try to do that in this problem, the washers are going to be oriented like this. So what's the issue? Well, the issue is the same function bounds the top and the bottom of the washer. That is, the inner radius and the outer radius are given by the same function. To give you an idea of what I'm talking about with the difficulties of working with the same function on top and bottom, let's actually see what those curves should be. Well, the outside curve here is, I need an x value, right? I need the x value of the outside curve and the x value of the inside curve, which means I need to solve this function for x. So if you do that, you end up with plus or minus the square root of y plus 2 is equal to x. So the top curve here is the curve given by root y plus 2 is equal to x. And the bottom curve over here is the curve minus root y plus 2 is equal to x. And just as a matter of practicality and calculation, most people prefer to work with powers and not square roots when they can. Sometimes the problem is even worse. So we'd like to come up with a way of constructing the volume of a figure like this that does not necessarily computationally work well when we use washers on it, and instead come up with a method that will work well when I have, say, the function defining a region where the same curve would have to be the top and bottom of my rectangle. So the obvious thing that presents itself is, instead of thinking about this being built this way with the rectangle that goes across and then cutting it into bread slices, maybe what we could do is cut it into rectangles this way, and then each rectangle that we spun around would be a very thin strip, like a tree ring almost. And if we could calculate the volume of these tree rings, then we could add them up for the tree rings that come across that build out this entire shape. So the method that we're going to use is called the shell method. And the basic idea is this. Let's look at the same example from the last page. If instead of thinking about this as being chopped into slices this way that are then rotated into washers, so the bad washers that would look like this, right? This is what we don't want. Instead, let's suppose that we're dealing with vertical rectangles instead. See what that does. So we're not going to use washers. These are washers. And instead we're going to use shells. So we're going to build a rectangle this way. And we're going to take that rectangle and we're going to rotate the rectangle around the axis of rotation. What sort of shape do you get out the other side? Well, it looks like this. It's skinny, and then it rotates around, and what you get out is something that looks like a pipe or a tube of some kind. So the idea that you've got is, can we figure out what the volume of this tube has to be? Right? This little thin shell here. Again, this is a shell because this is shell-like. It's tall and it's wide, but its width is this little tiny width in the circle, right? So how can I find its volume? Well, it's not a cylinder because it's hollow. So the sort of cheater idea that you use is if you cut it and rolled it flat, then you could just think of it as a rectangular parallelepiped. So that's the next idea. A shape like this. So this is a shell. Suppose that you just sliced it and you rolled it out flat. Well, what you end up with is a shape that looks like this. So you roll it out. What's the volume of that shape? Well, I know that it's skinny, and it's skinny in this axis on the top here. And that axis on the top corresponds to the width right here. Well, the width right there in the original picture, that was a little tiny increment in the x direction. So if you go back to the previous picture, you can see that this little tiny width right here was a dx width. So if I take that strip and I roll it around to get the shell, and then I cut the shell and I roll it flat, the skinny direction is this direction. So this direction right here, that's dx, or delta x. How tall is it? Well, on the problem that we had previously, we can see how tall it is because the height of our particular problem is going to be the distance from this top curve, which is y equals 1, to the bottom curve, which is y is equal to x minus 2 squared, and it's consistent the entire way across. 1 is always on the top, and x minus 2 squared is always on the bottom. Now, the particular height's going to vary depending on which x value I'm at. Okay? But that means for our problem that we have, say, an f of x on top and a g of x on bottom. As long as the f and the g stay consistent, then we can use f of x to determine the top of the rectangle and g of x to determine the bottom. And so the height is going to be their difference, f of x minus g of x. So that we've got width and we've got height. So I suppose I'll have to call this depth. So how long is it? To calculate the volume of this object, I need the height and the width and the depth. Well, the width of this shape is the same as the circumference of the shell that it came from. So since I'm dealing with a circumference, I know that that is 2 pi r is the circumference of a circle. Well, what is the radius? That's going to come from our axis of rotation. So in this problem, the axis of rotation was right here at x is equal to 0. And the distance from x is equal to 0 over to where that rectangle is located, which is the point x, that radius is x. So the distance of the location of the rectangle to the axis of rotation is just x. So this is 2 pi x, because this is 2 pi x around the top of the shell. So the volume of this shell is equal to height times width times length, which just turns into f of x minus g of x, 2 pi x delta x. So that is the volume of a typical shell. Then all we have to do is say where the shells end up. Where do we cut the slices that make these shells? How do we build the tree rings that build out the tree trunk? Well, in this particular problem, I didn't solve for it. It actually is between 1 and 3. But generally, to make this into an integral, you have to know where you start slicing and where you stop slicing. So the next slide, what we're going to do is we're going to take this idea and we're going to build it out into a formula. And then we'll start working through some examples to see how we don't need to memorize a formula. We just need to know the idea of taking these tree ring shapes, cutting them down into these little rectangular pieces, and using the standard length times width times height volume formula to add all those up. Okay, so what does the formula for these things look like generally? If you have some shape and you want to chop it up into these shell slices, right, or tree rings or onion layers, however you like to think about it. So let's go back to our original shape as a guide. I'm not going to use exact formulas here, but I will use it as a guide for what the formula should be. So we had a piece that looked like this, and over here, after we rotated it around the x-axis, it has another piece that looked like this. It's easy to see that this is where the first slice is made. The first slice that builds out a rectangle is x is equal to a, whatever the x value is that starts this region. And then chop, 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 all the way down to x is equal to b. And at every one of those locations, there's a little skinny rectangle that gets spun around the x-axis and turned into a shell. The typical volume of that shell, v, is going to be 2 pi x, although the x here, we have to be careful, that's only going to happen when the axis of rotation is the y-axis. So it's 2 pi times the radius of the shell, so the location of the rectangle in correspondence to the axis that it's being rotated around, times the height of the shape that we're looking at. In this particular case, that was 1 minus x minus 2 squared times the height, or the width of the shell. So this little skinny part right here, but the little skinny part right here was delta x. So this is my typical shell for this problem. And so the integral would be the integral from a to b of 2 pi x 1 minus x minus 2 squared dx. You should still be able to look at this formula and tell where all the pieces came from. So when you look at it, the 2 pi x at the beginning, that's the circumference. The 1 minus x minus 2 squared is the height of the shell. And the dx is the thickness of the shell. And with the integral, what you're doing is just adding it up from start to end. Okay? So if you actually wanted to finish this problem up the way we wrote it down, it would be the integral from 1 to 3 of 2 pi x 1 minus x minus 2 squared dx. And the reason is that this point right here is the point 1, 1, and this point right here is the point 3, 1. So your x values vary from 1 up to 3. And so all this is the shell method. Okay, so just like in the disk and washer method, the shell method is easier to figure out from implementation. Okay, so we made this specific to the setup that I have here. So generally, if you want a formula for these things, or a guide to how the formula should look, so sort of a general formula, so the general formula idea is going to be that the volume is equal to the starting place, the ending place, remember this is where the slices are, 2 pi times the radius of the shell times the height of the shell times d, either x or y, depending on what the orientation is. But the idea is that this is a circumference, this is a height, and this is a depth. All right, so in the next video, what we'll do is we'll look at some examples of how to use the shell method, and then an example of a problem where you can use either the disk method or the shell method, and that they're equivalent in many cases. All right, thanks.